Okay, so let's start our afternoon session. So this morning we had Paul Atzenberger from UC Santa Barbara, and this afternoon we have two speakers, Wenxiao Pan from Pacific Northwest National Lab, and then also Wang Lei will be a speaker at this session and later this afternoon. Thank you.
Okay, thanks. Okay, so after our intensive morning lecture about fluctuating hydrodynamics, this afternoon let's talk about some application examples in mesoscale modeling. I will using a different way to give you some idea about this center, what we are doing. So I will use several application examples to explain what different approaches can do for the mesoscale modeling. And the application area focus on this complex fluids and materials. Okay, so Paul already mentioned that we are in probably this scale, which is the mesoscale, from 100 nanometers to micrometers. And from this schematic plot, you can say, if we are in this scale, actually we have different ways to capture the mesoscale, either dynamic process or the target property. So first of all, you can still use continuum approach if you are interested in the mean field quantity. And also we assume the mean field theory is valid. If not, then this morning you already learned a lot about fluctuating hydrodynamics. You are interested in some stochastic process. You are trying to capture this effect of thermal fluctuation. Then you are going to use the fluctuating hydrodynamics. And also, those two actually based on you already have some of the governing equations. You know what actually is valid for describing your specific system. So if otherwise, if you don't know exactly what's the governing equations, the PDEs, and how you are going to do this modeling. So for this type of situations, if we know molecular details, you can do the cross-graining model. So typically we use here distributive particle dynamics. So let's start from some example that we can still use continuum approach. Okay, so this one is for some certain type of battery. So let's say this is the device. We focus on one of the part of the device, which is this air electrode. And then in the device scale, typically the length scale is in millimeter. And then we are saying, okay, if we zoom in and what's the detail actually inside the device? And then you can say, okay, probably a very heterogeneous structure. The mesopore scale structure is what you will see after you zoom in. And here, the typical length scale for the mesopore scale is from 10 nanometer to 100 nanometer. Of course, there are a lot of complicated process going on during the charge and discharge process. Let's make a problem simpler. Let's say, okay, we are going to capture the main process during discharge, which is about the diffusion of oxygen into this porous structure, and then chemical reaction is happening on the surface of this porous electrode structure. So this is the physical problem. And then, okay, so this is another way to explain this. So this actually picture are from experiment. So you can say this is really highly heterogeneous structure. And then actually during discharge, besides the diffusion, the chemical reaction here is you have two types of reaction mechanisms. One is this thin film growth. Basically, you have a very uniform thin film growing on top of the surface. And the other one is you will have this particle type of growth. This is not uniform, but it will allow you to grow very large type of reactive product. So this is basically give you some idea about the physical problem. Then you think, okay, how we can do from modeling perspective and provide some guidance in experiment. So first of all, you need to reconstruct the pore structure, because usually you only have some experimental data, and then you're trying to, when you do modeling, you want to capture the pore scale details, then you do the structure reconstruction. And of course, when you do the reconstruction, probably you cannot exactly represent exactly all the details of the actual structure. But what you can do is you can capture some main characteristics. So here, just give you an example. This is reconstructed structure from computer, and then we are trying to capture some main characteristics of those type of structures. And then, of course, you can say we can use construct the representative element volume, which is our pore scale modeling domain. So this is our representative element volume, which has all the pore scale details. Okay, let's say what's the governing equations. So on the pore scale, if we're interested in the mean field quantity, for example, the concentration of oxygen here, and then as I explained, this is about a diffusion and a chemical reaction process. So you can still use diffusion equation to describe the transport dynamics. At the same time, so here you have a reactive boundary, which is actually changing over time because you have some chemical reactive product is growing over time. So this equation actually basically tell you how this the pore structure, the surface is changing over time. So this is a dynamic equation for describing your moving boundaries. And then here is just a very, this is just directly bounded condition for your pore scale governing equation subject to those boundary conditions. So basically you can just solve the continuum PDE on this high heterogeneous structures. And then the next question is probably you can try to use different numerical solver as long as it's efficient enough to solve in this type of complicated geometry. Okay, then the next question is, so we cannot afford to run a fully resolved pore scale simulation for the whole device. So okay, we can model at a representative element volume in the pore scale to understand what's going on in the pore scale. But to do the prediction for the device scale, we want to understand the system level, okay, what's going on for this device, how we predict the performance. Then you still need to get information and trying to do upscaling to device scale. But the question is, without using any approximation and assumption, you do the volume average or volume integral over your pore scale. What you can get in general is just the integral equation, right? So each term actually still keep the integral form. So this is the general macro scale governing equations given your pore scale governing equations is determined. So we only have this. Of course, if you want to simplify this equation, for example, the people are using some Darcy scale equations that actually is simplified equation of the macro scale. They based on some of the assumptions. They can simplify or using an easier way to evaluate those integral. Let's say we don't have those assumptions, then we will keep all this integral. Okay. Then the question is, okay, I can calculate this or those upscaled information from my representative element volume of the pore scale. And then how I can design a numerical scheme that I can do the tightly coupling for this two scale. So here is some of guidance. So in general, actually here, you can in the device scale or in the system level. So let's assume you have all the grid points I minus 1, I plus 1 for your macro scale. And for each of the grid point, then I say, okay, I don't know anything. I just get information from my pore scale. So that's why I use a square representing there you need to get information from your pore scale. Okay, but this is a dynamic process. You can, and also the boundary is changing over time. So when you exchange information, you have to exchange over on the fly to get the information exchange between the macro scale and the pore scale. Okay, so here if you look at both the governing equations, So for the pore scale, actually the equation is not closed. Because for example here, the eta here, this is the system level quantity. So you don't know this when you do your pore scale modeling. And also the boundary condition here, C1 and C2 is not determined. And for your macro scale model, this is not closed either because those integral actually you need to evaluate from the pore scale. Then you can close your macro scale equation. Okay, so that's why you need to exchange information from pore scale and your device scale. And the data from pore scale to the macro scale will be something like this and another integral quantity. And then you need a constraint, or to close your pore scale equation, you need some constraint from the macro scale so that this two-scale model can be consistent. So this coupling will be on the fly, or will be in a concurrent way. So by this, you will couple, or you can do this upscaling dynamically. So yeah, so for this problem, I think this is based on the assumption that the continuum approach can be used to describe the transport dynamics. Of course, if you want to capture more complicated dynamic process, you can add in different complicated descriptions or whatever. So, but the key point here is, for this type of problem, you have a pore scale, you have a larger scale. If you cannot afford to resolve every details, you have to do this exchange information from one scale to another scale. And then in general, you can try to define such a numerical scheme to do this coupling. And based on specific problem, probably you can gain some more saving by doing this exchange over time. You can do this exchange less frequently and so on, but this is really based on your specific problem. Okay, then of course you can say, okay, we can do the simulation and then understand over the pore scale what we can understand during this dynamics over different time, how this reactive product is going on and changing the geometry. And then on the device scale, how this device scale system level quantity can be predicted after this upscaling and concurrent coupling. So, and then after you do the validation from the experiment, then you can also explore some of the prediction under different operating conditions, or different for different type of air electrode structures. You can try to provide some insight that how different it will be for the system level performance. So this is basically, yeah, this is the first application example. So I'm trying to make the point that given the assumption that the mean field theory is valid, and you are interested in the mean field quantity, and then you can still use the continuum governing equation to do the modeling. But for some of the problem, the difficulty might be you still need to do some coupling and exchanging information from one scale to another to do a full system level prediction. Okay, let's see another example. So here, the physical problem is this. So you have actually a protein molecule, and then you have some ligand molecule in the bulk solvent, and then you are trying to understand the ligand protein binding rates, or how the ligand and protein they are interacting. So okay, of course you can run a full all atom simulation for this, but probably it will be very expensive. So again, if you are interested in some average quantity, for example, how this total ligand protein binding rates over time, then still you can using the continuum approach to do the calculation. So here, the governing equation for this process will be this Smolakowski equation. Basically, it is a diffusion equation coupled with potential mean force. So the physical meaning of this is you have a diffusion of ligand, then you have an electrostatic accelerated diffusion by this term. So this term actually, because the solvent usually is ionic solvent, so at different ionic solution, this acceleration force, the potential mean force will be different. by this you can capture so different ligand, different concentration of ligand, how they will interact with your protein. Okay, here we assume the ligand is very dilute. Then the Poisson-Boltzmann equation is still valid. Then we can calculate this Poisson-Boltzmann equation to predict this potential mean force, and then at the same time solve this diffusion governing equations around the bulk solvent around this molecule, the protein. And here, what I want to point out for this specific application is, although you know, okay, this is a governing equation, this is we use the governing equation can describe this process, but the question is what kind of boundary condition you are going to give for the reactive surface. So it is known that for the in the far field, it is a directly boundary condition, and around the protein surface, it is a Neumann boundary condition. But on the reactive surface, in the past, people are using this absolute absorbing boundary condition, which is a directly boundary condition. But people found out actually this is not physically reasonable. So here, in general, you can say, okay, we are saying, okay, how about we use the reactive boundary condition, which is actually the Robin boundary condition on the reactive surface. And the physical meaning of this type of boundary condition actually is if you know the probability of the reaction is governed by this formulation, then here the alpha in the boundary, the Robin boundary condition actually is related to your probability of reaction. So if alpha is 0, then actually this is corresponding to Neumann boundary condition, then the probability will be 0. So if alpha goes to infinity, then this one will be 1. So it's the probability is just 1. So that's why it's absolute absorbing boundary condition. So that's why in general, actually, you should impose this Robin boundary condition to capture this probability. You are not sure it's 1 or 0 or something between 1 to 0. Okay, then we found out is okay, we can capture this ligand concentration at different ionic strengths. And also we can calculate this average reaction rate over time using this formulation. And then we found out actually using this Robin boundary condition, we are able to get very good agreement with experimental data. And then by this validation, then we can find out the backup this value of this alpha, and then take it to this probability formulation, and then tell people or experimentalists that what's the probability of the reaction given the condition that your ligand will react with your protein. So this is how actually we can use this continuum approach to understand such an application problem. The key here is the boundary condition. You need to impose the right boundary condition. Okay, so here, let's say these are some examples about this using the continuum approach, what we can do. And then you already heard a lot about the fluctuating hydrodynamics, but still I will give you some other examples. So let's maybe just review, although you already heard about fluctuating hydrodynamics, but I can give a quick review, make sure you still remember it. Okay, so here, the assumption here, so okay, let's start from here. So let's say we are actually looking at a dissipative flux. So this dissipative flux, given a momentum, for momentum conservation, it will be just stress. So the dissipative flux for velocity will be just stress tensor. So no matter what, so just in general, you have a dissipative flux. And then it is there, this is the constitutive relation for this dissipative flux. And X here is the thermodynamic force. And here then the assumption is we always can supplement a stochastic variable for my dissipative flux to capture the thermal fluctuation effect. So this is one assumption, but then I didn't do any other approximation here yet. So here, just given my constitutive relation, this is what we can do to supplement a stochastic variable. Okay, let's say if we specifically we only are interested in momentum conservation, then actually we are looking at the Navier-Stokes equation, right? And then we can specify those x will be the gradient of velocity, and this m will be my viscosity, because this is really about the constitutive law. And then you can specify the correlation for your stochastic variable. So this is, I think, what you have seen this morning about how the correlation of this stochastic variable. So here, of course, you have to make some assumption, which is you assume this is a Markovian process. Then you can simplify this correlation as this. And then we know actually here, actually I want to mention because it was not mentioned this morning. Actually, this is consistent with the statistical mechanics of molecular fluids. So because if you are familiar with some statistical mechanics, this is the Green-Kubo formulation. And then you can derive this Green-Kubo formulation from fluctuating hydrodynamics from here. So then you say they are consistent. And here you will say this consistent thermal scaling in the sense that it is proportional to your temperature, and delta function has the length scale 1 over r cubed for 3-dimensional, so that you know, okay, once you reducing your length scale, then you will say larger thermal fluctuation. So this is thermal consistency of this framework. And then, of course, you want to say, to use fluctuating hydrodynamics or any stochastic method, you probably are motivated by some application that I want to capture this stochastic process. So the typical problem will be this polymer, and it was also mentioned this morning. So here, let's say, okay, this polymer, we are trying to drive the polymer, we are trying to control the polymer dynamics in the channel, and then usually the polymer is highly fluctuating. So you have to overcome the thermal fluctuation, then you can control this polymer. So here we are saying, can we just design some of the hydrodynamic condition that we can control this polymer? Then you know, okay, we have this Peckley number is about what's the average flow relative to your thermal fluctuation or diffusion. So you need to overcome this thermal fluctuation, then you can manipulate this migration of the polymer. So this actually, I'm trying to give you some motivation why you need to capture thermal fluctuation. Okay, then here actually, it was mentioned this morning already. So basically, the solvent is explicit solvent, and then each of the polymer bead is the same as the solvent particle. They have the same length scale. And then for the polymer bead, they are actually interacting with some of the spring force. So here, I just simply use a linear spring force. You can, of course, change it to Finney or Worm-like chain and so on. But then the numerical scheme will be the same. Just you have the solvent particle, and you have the bead same as your solvent particle, but those beads are also interacted with spring force. So this is how you model such a system. And then, okay, if you want to do some application in the microfluidics, you can try to design the boundary condition. So here we're trying to design the boundary condition which is charged in a patterned way. So we change the charge, the surface charge on the channel, and we also change the slip length on the boundary wall, and trying to manipulate the flow behavior inside the channel. So you can say by doing this type of patterning design on the boundary condition, you can get your flow behavior is very different. So then you can imagine using those flow, you can manipulate your polymer in a real microfluidic design. So this is the application that motivate you to consider using fluctuating hydrodynamics. Okay, this is another one. Okay, so here, this is the physical problem. So if you have two types of fluid, and the lighter one is on the top and the heavier one is on the bottom, and they have different concentration, and then you have the concentration is diffusing from the bottom to the up through the interface. So basically, this is the stochastic diffusion process. And then this is actually observed in experiment in a microgravity situation. So they observe this really giant fluctuation in concentration field. And then this is also tells you, okay, if I really want to capture this fluctuating front of concentration, I do need to use this stochastic equation to capture those fluctuating front. And here, since this is a diffusion of concentration, then we are gonna use this stochastic diffusion equation. Again, similar to this Landau-Lifshitz-Navier-Stokes equation, you will have this stochastic variable in the concentration field. The difference between the mesoscale modeling here with the continuum modeling is, here you cannot just use the concentration equation, right? The diffusion equation. You have to couple it with your Navier-Stokes equation. The reason is, although now the average flow is 0, so you have just diffusion, you don't have average flow, but you have a thermal fluctuating velocity. So you still need to couple with this Landau-Lifshitz-Navier-Stokes equation to give you the thermal fluctuating velocity. So that's why in mesoscale, if you want to capture this fluctuation, you need to solve this equation coupled. But you notice that those two stochastic variables, they are not coupled. This is because if we apply the current principle, if those two variables they don't have the same tensor property, then their stochastic variable can be decoupled. That's why you have this stochastic variable for a Navier-Stokes equation and stochastic variable for a concentration diffusion equation. Okay, so this is the equations that we are going to using to capture this fluctuating concentration field. And then another thing we need to know is, because now they are coupled, so they will be different from you are using just the macro scale deterministic diffusion equation. The reason is your fluctuating velocity will accelerate or enhance your diffusion. So your effective diffusion coefficient actually are from, this one is what is from your fluctuating velocity, basically the self-diffusion. And this one is what you specified in your diffusion equation. So actually the effective diffusion coefficient will be composed by these two components. So that's why in mesoscale modeling, what you specify in your diffusion equation, this one should be renormalized by your actual diffusion coefficient minus your the self-diffusion coefficient from your thermal fluctuating velocity. So this is also thermal consistent because you can think if you all the way go down to the molecular scale, then actually all the diffusion are from the self-diffusion. So this one you can specify 0, then this one will be equal to each other. So basically all the molecular motion gives you the diffusion. And then if you go all the way to the continuum scale, then this one will be 0. So then you just specify the diffusion coefficient into your fluctuating diffusion equation. So this is actually also tells you, this framework gives you this length scale consistency. And here, of course, you can do some, after you have the numerical solver, then you can try to capture this fluctuating front in terms of wave number and check to validate your numerical solver. Okay, I guess we have plenty of time. Do you have questions so far? So basically we covered continuum approach and fluctuating hydrodynamics. Both are based on the assumption that we have the Goldman equations. Then if we are interested in mean field theory, we can still use just continuum PDE, but if we are interested in thermal fluctuating effect, then we probably can go to this fluctuating hydrodynamics. And I give you just 2 examples for each of the approach. Any questions so far?
So we're not getting too many questions from the audience so far. Maybe.
I do have a question.
Okay.
So I'm interested in the biomedical, the diffusion part. So I was wondering, I think you didn't. Do you put the drift term there?
Yeah, this is the drift term.
So drift term. So if you have the drift term, but you said like alpha is the is the reaction rate, right? So in my mind, you are talking about, say, in a chemical reaction, that's the reaction rate from compound A to compound B, right?
Mm-hmm.
And does that mean like this reaction, you want to say this reaction rate has nothing to do with the drift? I mean, say if I have, so I'm not sure and what kind of drift you are putting here. Say if I have like some like electrical charge and I put like, put the particle or the chemical into the electric field, I think it will affect the reaction rate in my mind. Or you are talking about pure diffusion. I don't. So this part I don't really understand that.
So
well.
I mean, yes, I mean intuitively, yes, I think you are right. Probably this alpha can be dependent on ionic strength. For example, this drift term actually is from Poisson-Boltzmann. This is the electrostatic drift term. So that's why actually this term is dependent on ionic strength. But okay, we numerically and also experimentally, what they found actually this is at different ionic strengths. There are experimental data measured.
Okay.
And then what we found is, okay, we put alpha as a constant for different ionic strengths. It seems they gave, at least good agreement from our numerical test. But I don't know if we change it to a ionic strength dependent parameter, it will improve the agreement or not. Yeah, I don't know, but
Okay, thanks.
I mean, physically, it should be more
And
reasonable.
alpha can be coordinate dependent also, right? You can test.
Mm-hmm. Yeah, that's. Yeah, actually, yeah. Yeah, this one, yes, we treat as a constant, but yeah, you are right. Probably because our reactive surface is simple, it's represented by a sphere. So we treat it as a constant is okay, but if it's actually a very complicated reactive surface, then alpha should be a spatial dependent variable.
And then you can take into account some of the things he said.
Yeah.
Yeah, as I'm
that's
saying, like if you intentionally put into like electric field like different, like if you put external electric field,
Mm-hmm.
it might give completely different like results. Right?
Mm-hmm.
Give her the field and she'll try it out.
Alright. Okay. That's all.
Any other questions?
I'd be interested how, when you were talking about the concurrent modeling, how you handle like error quantification between the two different scales.
You mean how to control error when we do the coupling?
Yeah, and maybe that, and I mean, your model is outputting one thing, but you have two different scales and they have two different levels of error. So I'm just curious how you.
So the error actually come from three sources. One is the pore scale. So that one actually is easy. As long as you use accurate enough numerical solver, then you can control the accuracy. So the macro scale actually is also okay. It's really depending on numerical solver. So I guess the main question is how to control the error when you do the coupling. So here, that's right. So here actually you can say when we do the constraint, we actually from the macro scale, we get the concentration, the average concentration, and also the gradient of the average concentration. And then this actually, using this, we compute the boundary condition for the pore scale. So this is just first order approximation, of course. So if we want to improve it, then we have to use higher order approximation to get the boundary condition for the pore scale. Yeah, that's yeah, but for this actually, it's exact because we didn't make any approximation. We just exactly compute the average from the integral and then pass to the device scale. We didn't simplify the macro scale equation.
Okay.
Yeah.
Wenxiao, I have a question. So you kind of connected the Robin boundary condition with the probabilistic. Was it because there are people who are doing sort of non-local calculus, like fractional and others, but they try to actually do that, but in a systematic way. So is it some? Can you go over that again? Because Is it something deep, or is it something that you sort of did ad hoc and it worked?
Okay. Yeah, I didn't do no local calculus for this. So, but so the reasoning behind using this is, okay, this actually delta t over delta x is given the certain time interval and over certain distance, and what is the probability of this reaction. So this is actually approximation. Maybe Greg Shanter knows this better. So we got this from statistical mechanics to approximate, given those time scale and length scale, what will be the probability for
Yeah,
reaction.
just a local theory.
Yes.
So where are we on non-local calculus for this type of
I don't
problem?
know.
George, where are we? Can you do it?
No, there's like, including the people at Sandia actually, who have been
That's the thing to do.
been looking at that. This is the interpretation, how, to relate that to the Robin boundary condition directly. And the coefficients of the Robin boundary condition will tell you that. Like when you jump outside the domain, because you don't deal with a boundary, right? You deal with a scheme.
Yeah, that's right.
Volumetric,
Yeah.
like a volumetric constraint. So those coefficients could be related to the size of your domain and the probabilities of jumping. So you have like a Dirichlet or a Neumann or anything in between, of course. So but
Okay.
it's not the routine. It's just that I kind of made the connections
Yeah.
since you mentioned it.
Yeah, maybe something then we can discuss with Mauro later offline.
I mean, have you looked at like first passage time problems, like the Dinkin formula, and relating that? You could relate that to your Robin boundary conditions.
But
I didn't do that, but yeah, probably that's also.
I think they assume this though. The mean.
Yeah,
It's
but this is
exactly-
first passage, I
That
guess.
that is the mean first passage time as
Yeah.
well.
Well, I mean, what I'm suggesting is to start with a stochastic model.
You mean the Monte Carlo type of
You can do a lot of
computation
that,
for,
And I think you can derive the
yeah.
Robin boundary condition for the PD for the mean first passage.
Okay. Okay, then I guess let's move forward. Okay, then let's say we are already discussed about continuum approach and fluctuating hydrodynamics. And then let's say, okay, you have something that very complicated. You have polymer melts, you have some nanoparticles with polymer, then you have some of the assembly of certain type of molecules. And yeah, this is actually from Peiyuan, actually. This is a dendrimer assembly. So for those kind of complicated process, probably you don't have the governing equations, or at least you are not sure what type of governing equation are accurate enough to model those kind of process or system. Then, but at the same time, you know some of the molecular detail for those systems. And then probably you want to use a different approach. So that's what we cut. They can use this bottom-up approach using this distributive particle dynamics. And here, okay, I will talk about the single particle distributive particle dynamics. But other lecture, I guess tomorrow, other people will talk about more about the distributive particle dynamics. So here, in this framework, actually, this is very similar to molecular dynamics. You will have your system, all the particles, and then the system, you will have the quantity to describe the system, including the position, rotation matrix, and linear momentum, and rotational or angular momentum. So this is how you describe such a system. And then for each of the variable, actually, they are governed by something like the Newton's second law. You calculate their interacting force and then to change their momentum. So this is how this framework is governed by those variables and equations. And here we conserve the linear momentum and angular momentum. Yeah, but by guarantee those paraforce are antisymmetric. Okay, so here I want to mention a couple of things about this framework. So first of all, it is different from coarse-grained molecular dynamics. So because this CGMD actually only considered the mean force of the two coarse-grained particles. And it's also different from the Landron dynamics, because Landron dynamics has the mean force, and then for each of the coarse-grained particle, they assume the same random force and the distributive force and the random force. So they don't consider a correlation between two coarse-grained particles. It is also different from the standard distributive particle dynamics, because the standard DPD consider the correlations of random force between coarse-grained particles, but only the parallel component. So here, in this framework, we consider both parallel component and the normal component, basically the full component of this correlation. And then we can conserve both static and dynamic properties using this framework. So I guess tomorrow, George and other people will talk about how this can be interpreted in terms of this Morris-Wanzig projection. Basically, you have three terms, and then you need to evaluate those three terms. And then this framework, actually, you can understand this framework by we actually have all the terms and just make some approximation to evaluate this correlation term. And then, okay, in this coarse-graining framework, there are two approaches. So one is, okay, we use some empirical force field with free parameters to be determined to capture target properties. So it is very similar to you use in MD simulation, you use some empirical force fields, and then you are trying to capture some target properties. Probably you leave some free parameters to be determined later. So also you can do this forward coarse-graining procedure, but of course this is very challenging. And then again tomorrow, then this will be covered. They can directly from MD using this Morris-Wanzig projection and trying to calculate each of the force field. Then you don't have any free parameter to be determined. So these are two different approaches, but I will just focus on the first one. And then using this approach, this single particle distributive particle dynamics, we can do the following application examples. So the first one is this for the colloid. So let's say the motivation of this is you have colloid are going through some of the porous media. Actually, the first example, the battery, we can put this, actually incorporate this model into that problem because there are a lot of this colloid catalyst going on during discharge or charge process, and those catalysts actually also contribute to the system level performance. So let's say you have such a system, but here we consider the colloid is Brownian and non-aggregating and non-rigid. So let's consider non-rigid colloid. And also they are spherical. So given such a suspension of the colloid, we can use the single particle DPD to capture this dynamic and static properties for such a system. So let's say we focus on very concentric colloid suspensions. So you can see it's very concentric colloid suspensions. Then we can calculate the rheology of this suspension. So this morning, actually, for example, you can use this Least-Edwards shearing to calculate each of this viscosity at different shear rate, or you can use Poisson flow, actually, using this parabolic flow profile to calculate this viscosity at different shear rate. So this is, we use different approaches to calculate this rheology of a colloid suspension. And also you can try to understand the phase transition. So when you give some shear of a very concentric colloid suspension, then you can say, you can find this phase transition when you apply some shear flow overcome the thermal fluctuation, then you can see this phase transition. This is after phase transition, the order structure. If you calculate this what's that? It's a radial distribution function on projection of this function on a different plane, then you will say this order structure of the colloid suspension after the phase transition. So with this framework, my point is we can try to calculate or capture the dynamic process of this concentric colloid suspensions. Okay, another thing is urinate the clay, we are trying to understand if the surface tension can also provide some interacting force to accelerate this self-assembly of colloids. So basically, this is some schematic plot showing how the surface tension will be important for the self-assembly. Then we can introduce some interacting force, which is in long range it is attractive, in short range it is repulsive. And here we can also approximately, using this density-dependent potential function, to incorporate this many-body effects when we do capture this surface tension. So here, this example is about if you have a droplet, and then you give some perturbation, you have a cylinder of the droplet, then you give some perturbation, then you will find this pinch off of the droplet. So this is a very classical path for this study this surface tension. Then actually you can calculate from the cylinder of the droplet to the final breakup. So all this time regime, the different scaling regime. So this regime actually is the stochastic regime. So that is when this thread is already very thin, the stochasticity is very important, then you will say this scaling will change from this one, and this actually is in continuum regime. So we can capture this stochastic regime. Actually, it changes a lot, the scaling law changes a lot from the continuum to the stochastic regime. And then this model can capture quantitatively this scaling law. After the thread is very thin, the stochastic effect is very strong. And also, if you have the solid boundary, you want to capture this liquid, vapor, and solid interface, then here it also shows you, given a different Bond number, you can capture those totally different wetting behaviors. Okay, so this is also, if we, under this single particle DPD framework, if we introduce some linear mapping operator. So basically, before the Cold-Spring model, each of the particle is spherical because the interaction force is isotropic. If we introduce, we can calculate this linear mapping operator. Basically, it is calculated or defined by the rotation matrix and the shape matrix of your particle. So what we can do is, for example, the ellipsoid particle, it's very easy to calculate its shape matrix. So using this shape matrix, and we calculate the rotation matrix over time, then we can define this linear mapping operator. Then if we apply this linear mapping operator in front of our interacting force between the spherical Cold-Spring particle, then we can model this ellipsoid particle, so the suspension of ellipsoid particle. So here, just give you example that, again, we are interested in very concentrated suspension of ellipsoids, and the ellipsoid is non-rigid. So here we capture the transition when you increase the concentration or you increase the aspect ratio of the ellipsoid. Okay, so, and also this is the last example about using this single particle DPD, that we can use this model to construct some low-dimensional representation of some deformable entity. For example, a red blood cell. We can use this single DPD particle representing a red blood cell using a less number of the particles and trying to capture a bulk property of a lot of red blood cell suspension. And then we can use it to do the efficient design for a microfluidic device. For example, if you are trying to do the separation of red blood cell using a microfluidic channel, then you can use this model, quickly design qualitatively. Okay, this type of approach strategy can give you efficient separation of red blood cells on the other side. And also we can trying to capture some of the aggregation or assembly of red blood cells or some deformable other type of entities, how they aggregate, how they grow, and how they affect the rheology of the suspension. Okay, all right. So I guess this is the last example. So overall in CM4, actually, we focus on the mesoscale, And we are trying to understand at the mesoscale, we are trying to understand the transport. So we mentioned a lot about hydrodynamics, diffusion, and so we are interested in the transport and also the broken symmetry. For example, phase transition, and phase transition can be a good example about broken symmetry, and also fluctuations we mentioned a lot. And interfaces and boundaries, especially if we have a moving interface and moving boundaries, and how we deal with those kind of problem. And also the inhomogeneity, because in such a scale, lots of details actually cannot ignore, or cannot just simply average those out. So we need to deal with the inhomogeneity. And then this is overview about the CM4 application and how we deal with the application using this strategy. So I guess with that, I will finish my lecture.
Okay, thank you very much. So any questions?
I have a question.
Great, yeah.
So, this case of broken symmetry, is it something that happens dynamically in the problem, or is it as the system evolves?
Yes, so yes, I think the answer is dynamically.
Okay.
For example, in this one, actually, if you start from isotropic phase, so everything just randomly, orientation is randomly, and then after equilibrium, it will fall. It will actually has this kind of order structure formed.
Okay.
In another case, actually, if you introduce some of the flow, like the shear flow, then the shear flow also will help to the structure to be ordered, aligned to each other.
So all these are somehow non-equilibrium phenomena, right? I mean, you have to capture this transient behavior. And so what kind of, do you need any memory terms to do this?
Yeah, that's a good question. For the phase transition, so far, this one actually we have a quantitative comparison. Okay, here first of all, this is the soft, non-rigid ellipsoid particle. So there's no validation for exactly non-rigid ellipsoid phase transition. Those are the data are from the very rigid liquid crystal type of ellipsoid particle. And then we do the comparison, then we found actually we only qualitatively agree. So then the discrepancy can be from, one is this memory kernel effect, or one is we are actually here, it's not the rigid crystal particle, this is just the soft colloid particle.
So the discrepancy that you get is, you say, quantitative discrepancy.
Right.
In what sense? I mean, you get the transition, but you don't get the times that it happens. You don't get.
For example, yeah, exactly.
Okay.
So, for example, this is when we increase the aspect ratio, but at what aspect ratio we will see the order structure. We can calculate the order structure factor representing this order structure, but at what exactly the aspect ratio it will form this order structure. So those has some discrepancy.
So I have a question about this WD of R. So how do you calculate this function, or is it how do you fit it? So this is a function that
This W,
right. It scales down your interaction, right? As a function of R.
Right. So, for example, in this function, in this interacting force, this is conservative interacting force. So actually, it basically will determine what's the salvation layer of each single ellipsoid particle. So you can run a equilibrium simulation, and then look at the salvation layer around this ellipsoid particle, and then calibrate the parameter in this kernel function.
But what about the WD is for the DPD friction, right?
Yes. In this one, we actually use the diffusion coefficient. We can calculate diffusion coefficient with this, and then we need to calibrate if we exactly capture the diffusion given a ellipsoid particle. size of ellipsoid particle.
Yeah, but the WD is an actual function, so diffusion is just one, you can fit one parameter.
Oh,
perhaps.
yes. So the function form actually is we assume that's fixed. We're only trying to
I see.
calibrate the free parameter.
So it's just like a linear function?
No,
or what
this
it?
is actually exponential function here.
Oh, exponential function. Okay.
Yes,
And there's one parameter that you tweak.
right.
All right. Any other questions? Okay, so I guess we